Good morning, class. We are looking at section 3.10, linear approximation and differentials. Let's quickly cover what we just did before, and then we move on to the new stuff. So, we are looking at linear approximation and differentials. There are differentiation formulas that we should be comfortable with. Okay. The idea of a related rates, recall that you have an equation that relates the two quantities, then you differentiate implicitly, and with respect to the chain rule, dy dt becomes dy du du dt. Logarithmic properties are here. You want to be able to come up with the logarithmic properties in general for natural log as well as common log. The linear approximation was explained here. If you look at the graph, the run is delta x. The rise, it depends, you're dealing with the function. We call it delta y, or the secant line, the same thing. But for the tangent line, we call it dy. dy is the differential for y, and it's equal to f prime of x dx. It can approximate delta y. Linearization, as it was mentioned, it simply means find the equation of a tangent line. And we did this example, we calculated dy and delta y, and we basically plugged in. dy is f prime of x dx. Delta y is f of x plus delta x minus f of x. In this example, we use the differentials to find the approximate change, which means we were looking for dA. A is the area of a circle in this example, pi r squared. Delta A was the exact change. You would have to calculate the area for the radius of 1.3, for the radius of 1.4, their difference would be the answer. So let's go to the, and now this was covered. And let's go to the new stuff now. Okay. And so let's put this in slide mode, and we're going to go to the new example class. So this was covered. All right. So here's the new one. And what we want to do, class, we want to come up with sine of 31 degrees. Okay, we are approximating. Remember that we are approximating. So let's see how we do that. Okay, so approximation requires the use of dy, okay, or the linearization. We'll look at both cases, see how it's done. Dy is very simple. First and foremost, f of x is sine x. Find f prime of x. So f prime of x or dy dx is cosine x. Not a big deal at all. Okay. Now, what is dy? Dy by definition is f prime of x dx. So cosine x dx. That's all there is to it. Done. Now, the moment you hear linearization, just remember what? The point slope, class. That's all you really need to remember. This is what linearization is all about, but you don't even have to memorize this formula or remember it. Just remember the point slope, okay? Remember the point slope. So you need a pair, okay? So x is pi over 6, everybody. X is pi over 6 is given, okay? So plug in here. What is y or f of x is f of pi over 6. I hope you know that sine of pi over 6, okay, is equal to 1/2. Okay, so that's your pair. Okay, so plug in, that's your pair. Now, what about the slope? Okay, so that's the pair. Okay, x of 1 and 1. What about the slope, m? Well, f prime is cosine x. We already found that. So plug in pi over 6. And that gives you the slope. Okay, so the slope uses f prime of x. We plug in pi over 6, and the pair x is given as pi over 6, sine of pi over 6 is 1/2. So this is fairly straightforward. So what do? We write this formula and we plug in, everybody. Write this formula, the point slope. So y minus 1/2 equals m square root of 3/2 x minus x of 1 over pi over 6. So point slope, plug in, point slope, plug in. So you distribute the square root of 3/2, you get square root of 3/2 x, you multiply it by this one, you get square root of 3 pi minus that, okay? Over 12, and negative 1/2 moves to the other side is positive 1/2, okay, class? So the y, or f of x, in this case, L of x, I should say, okay, y or L of x, so I actually change that to L of x because it's a linearization class, so I want to, so change this to L of x. Okay, by this f of x, we mean the function that represents the tangent line, okay, so change it to L of x to be on the safe side. Okay, that's it. This is A and B. Now, we want to find sine of 31 degrees. By the way, if you want to find sine of 31 degrees, remember, you know sine of 30 degrees, and by the way, everybody knows that pi over 6 is 30 degrees, right, class? And then you can approximate sine of 31 degrees, sine of 29 degrees, sine of 32 degrees, something pretty close, okay? So what do we use? Remember that f of x plus dx or delta x is f of x plus dy. Everybody remembers that, okay? And so we want to approximate that, f of x plus dx. That one is part of the homework. I put cosine of 28 degrees. So we want f of x plus dx, okay, everybody, where dx is 1 degrees, but remember, you really have to change that accordingly, everybody, okay? You have to change that accordingly. Okay, so what is f of x? You replace it with f of x, which is sine x. Okay, you replace it with sine x. So f of x, sine x. So replace the f of x. What about dy? Let's go back here. We found dy in part A. Okay, so put it here. Now, it's important to understand in this case, okay, x is 30 degrees and dx is 1 degree. Okay, now, of course, 30 degrees means pi over 6. 1 degree means pi over 180. I hope everybody remembers that, okay? So we need to go with the radians for this to work. Okay, so sine of x, okay? So that means sine of 30 degrees, but we're going to put pi over 6. Cosine of x, that means cosine of 30 degrees, that means pi over 6. They really don't make that much of a difference if you put degrees or radians. What makes a difference is dx. You don't want to put 1. That's the idea. Okay, that's the one you want to be careful. So what do you want to put there? Pi over 180. Okay, so 31 degrees is 30 plus 1. Okay, 30 is pi over 6. 1 is pi over 180. Okay, and so sine of pi over 6, we know the answer, 1/2. Cosine of pi over 6, okay, we know the answer, square root of 3/2. And pi over 180 is 3.14159, continues indefinitely over 180. In other words, what I'm saying is this. You replace this one with 1/2. You replace this one with square root of 3 over 2. And then pi times pi over 180, the denominator is 180. and the denominator is pi 3.1415 and you keep on writing. Now, of course, you use a calculator, and as you can see, the answer is very close to 0.5. It's 0.5151. I hope everybody's clear as to what's going on here. All right. If we want to go with the linearization, L of x, remember what we want. We want L of x is 31 degrees. So let me just, so you use this formula L of x. What is x? X is 31 degrees. 31 degrees is what? 31 pi over 180. I want you to know that. So therefore, you replace the x with 31 pi over 180. So square root of 3/2, x is 31 pi over 180 minus square root of 3 pi over 12 plus 1/2. Now you use your calculator, and class, you get the same answer. Okay, I didn't put that, but you get the same answer. Okay. By the way, I think you know that, but I'm going to just remind you that degrees over radians, okay, it's the same as 180 over pi. This is one formula you can use to go from degrees to radians and vice versa. For example, degrees is given, okay? You put 31 here, you find the radians. Or radians is given, you put it here, you find the missing degrees. This is a very simple formula from trigonometry. I hope everybody's comfortable with that. All right. The next one is, we want to use the differential to come up with 51 squared. First of all, squaring it is very simple. Everybody knows that. You can do, for example, algebra 50 plus 1 squared. 50 squared is 2,500. 2 times 50 times 1 is 100, makes it 2,600. And then 1 squared 1 is 2601. That's a precise answer. But when we say approximation, we need two things. First, we need a function. So what function do we have in mind? So 51 squared, what is the action, the operation that is taking place? 51 squared, so f of x is x squared. The next thing is, we want to find the closest number we can think of to number 51, such that we can easily square it in our head. Okay, can anybody think of a number close to 51 we can square easily, class?
50.
Which is 2,500. Perfect. So that would be the choice. Now, what about delta x? We are going from number 50 to number 51. Their difference is +1. So I want you to pay attention to how you find delta x. We are going to start with 50 and we're going to arrive at 51. So therefore, we are going up. However, if we were interested in finding 48 squared, I hope you see that dx or delta x is -2. Okay, I want you to see that. Of course, we're not going to do that. You're more than welcome to do this at home, but understand what's happening. Delta x for 51 squared is +1. Okay, so we are going to use this approximation. So first we need f of x. We came up with that. Now we need dy. In order to get to dy, we need to find f prime of x. This is easy. X squared gives you 2x. Okay. And so f of x plus delta x is f of x plus dy, and f prime of x is 2x. So dy is 2x dx. Now replace this. Okay. F of x with x squared and dy with 2x dx. Practically, you're done. Replace the x with what? 50, same here, and dx with 1. So when you plug in and you finish the job, by the way, f of 51, that means f of x plus delta x. Remember what this is, class. This is x plus delta x, 50 plus 1. And you end up with 2,600. I had already explained the exact, fairly simple. Now, Let's do the linearization on this also, just in case. Not that you have to. So what do we want? We want to find the equation of a tangent line using the point slope. So first understand, y minus y1 equals m times x minus x of 1, okay? And y1, you can move it to the other side. So what is y1? Remember, x is 50, plug it in. That means f of 50 is y sub 1. I hope you see that again. You're looking at f of x equals x squared. Choice of x is 50. So the pair would be 50 comma 50 squared. So y sub 1 is 50 squared, or f of 50. Plus, now, what is m is the slope. F prime of x is 2x, replace it with 50. That's how you find this slope. So I hope you see this is a point slope. Also, I've written it in this format just to refresh your memory of what you have seen in calculus. So understand they are the same. You can even completely ignore that and go with this, write the pair, write the slope, plug in. So when you finish the job, you get this one. And by the way, this is 2500 plus 100x minus 5000, and they add up to 100x minus 2500. Now, so this is L or L of x. Now plug in 51. Plug in 51 and it gives you exactly the same answer as you found here. They should. The linearization and differentials, they will give you exactly the same answer, class. Oh, I hope everybody can see that. Okay. Here's the next one. We want to come up with the square root of 27. We need two things. We need a function, and we need a number close to 27 such that the square root can be easily calculated in our head. Just read the question, square root of 27. What function do we need? So f of x must be what are we doing? What action? What operation? Square root of 27. So f of x must be square root of x. What number can you think of that is the closest number to 27? And you can take a root easily. Anybody? $25, because square root of 25, everybody is supposed to know it's 5. And so what is delta x? We are going to go from 25 to 27. Delta x is 27 minus 25, which is 2, positive 2. Positive 2. So what do we want? F of x plus delta x is f of x plus dy. So we need f of x, we have it. We need dy. By now, you know that the derivative of square root of x is 1 over 2 square root of x. I hope everybody remembers that. And one easy way is to rewrite this as x to the power of 1/2. So the derivative becomes 1/2 x to the power of negative 1/2. And so dy is the same thing times dx. So f of x is square root of x. And then dy is 1 over 2 square root of x dx. Okay. Again, remember, and I can write it at top here if you want. This is 25, everybody. Okay, plus 2. Again, if it's negative, such as square root of 24, you would write 24 plus negative 1. So pay attention to the sign of delta x. And so plug in, replace the x with 25 and dx with 2. Okay, f of 25 plus 2, or f of 27. You know this is 5, you know this is 5, 2 and 2 cancel each other, 5 plus 1/5. And 5 plus 1/5 is 5 and 1/5, or 5.2. Again, For the sake of argument, if you were to find, let's say, square root of 24, then delta x or dx is -1, just as an example. So you want to pay attention to the function that you need and the value of delta x, whether you have a delta x which is positive or negative, okay? So you want to pay attention to that, okay, everyone? All right, let's go to the next question. Could somebody be kind enough to read this one for us, please? Okay, wow. The total cost is given as C of V, okay? V is the average velocity, average speed, okay? Is given as such, okay, class? We want to find the approximate change in the total operating cost when the average speed is increased when we go from 55 to 58 miles per hour, okay? So when we say approximate change, okay, we really want to change in the cost, okay? So delta C or DC, and that is by the approximation. So the V is 55, delta V or dV is 3V, and we want delta C, okay, or DC, which is C prime of V times dV. In other words, look at this one. We are looking at, let me just put it up here. We are looking at dy equals f prime of x dx. We want basically dc, okay, class? Remember, delta C is a precise, okay, delta C, you plug in 58, you plug in 55, the change is the answer, done. But DC is what we are going to approximate it by because it says approximation. So simply put, differentiate, multiply by dV, and plug in. Differentiation is very simple. I'm assuming everybody can differentiate this easily, okay? And by the way, class, your independent variable is V. So that gives you 1. And this one, you can write it as 4,500 V to the power of -1. Then it becomes 4,500 times -1. If you are differentiating this, by itself becomes 4,500 times -1 V to the power of -2. And this whole thing is second piece. So what is DC? The same thing times dV, okay? The same thing times dV, okay, class? So actually, maybe you want to write dV first and then replace it with 3, okay, class? So you want to write it as dV and then times, replace the V with 55, dV with 3, and evaluation will give us -1.46. The total operating cost decreases by this much, okay? The total operating cost decreases, okay? The total operating cost as a result decreases, class, okay? And so that's important to see. It decreases by this much. All right, so I hope it's clear to everybody. So let's quickly recap. Okay, we are basically finding DC. Okay, everybody, we are finding DC. Okay, and DC is what you found here on the right side times dV, and then plug in. And because it's negative, class, we say decreases, okay? Because it's negative. That's important for everybody to see, okay? So I hope it's clear to everybody. All right, let's move on. All right, so we want to verify the linear approximation is this. By that we mean find if this is the function class, if this is the function f of x, that's the idea. This is the function f of x. Prove this is its linearization L of x. In other words, if this is the function, find its tangent line, okay? At what point? X equals 0 or A equals 0. That's the idea, okay? So you plug in, you find the pair, and so on and so on. So it's very straightforward. I hope everybody can see what we are trying to do. The next part really requires a graphing calculator. I explained the concept, you don't have to worry about that. But the first part, it simply put tells us, okay, find the what? Find its tangent line. This is the function. This is the function, okay? And we want to show that y equals 1 minus 3x is what? Is its linearization, okay? So that's the idea. Tangent line. All right, so let's start with f of x, okay? So how do we differentiate that? Okay, minus 3 comes in front, then you raise it to the power of -4, then the derivative of the inside is 1, we just don't write it. Okay, so this is f prime of x. You can put the -4 at the bottom, you just keep it in the same manner, it doesn't matter. Because we need two things now. We need a pair, which means x is 0, plug in. Okay, plug in, you get 1 plus 0 to the power of -3, or 1 to the power of -3, simply 0, 1. And the slope, the same thing, plug in, and the slope becomes -3. So first and foremost, plug in. You plug into this, gives you the pair. You plug into this, gives you the slope. And because this is y equals mx plus b, because this is the b, you just don't have to use the point slope. I hope it's clear to everybody. Okay, I hope it's clear to everybody what we are trying to do. Okay. All right. So this is the main part, and you're done for all practical purposes as far as I'm concerned. Okay, class? You are done. The second part says, okay, let's find the values for which the linear approximation is accurate within certain amount. Okay, so now it requires the use of a calculator as follows, class. Okay, so first and foremost, we want it to be accurate within certain amount, so we add and subtract this one. Okay, so we want 1 minus 3x or minus 3x plus 1, however you want to put that, it doesn't matter. We put it in descending order here. So this one, we want it to be the same as this one, but within 0.1, so minus 0.1 and plus 0.1. And in this case, there is really nothing you can do. You graph this one, you graph this one, okay, and you graph the middle one. When you graph him, okay, when you graph him, here's how they look like. So take a look at how they look like, class. Look at those points. So those are the points where the graph of this line crosses the other two functions. Okay, what are the functions? One of them is f minus 0.1. Remember, this is f. Let me just put f at top of this. This is the f of x, class. So you are adding and subtracting 0.1. And so wherever the graph crosses, okay, it doesn't matter which ones, okay. In this case, over here, let me just use a laser pointer. Over here, so you want to locate this x coordinate, and over here, you use a graphing calculator, and it seems if you do the zoom, it reads the x coordinates as those numbers. You don't have to worry about that too much, but I just wanted you to be exposed to that in case you come across a similar question. All right. We want to find the differential for these functions class. We want to find the differentials for these functions. So basically, you differentiate the first step and you completely ignore about the differential. Whenever you're done, so you want to do this. Whenever you're done, you tag along the dx. So in this case, the independent variable is u, so you tag along du. In this case, you tag along d theta. So to differentiate the first one, you need to use the quotient rule. So first, let's find y prime or dy du. Okay. So the derivative of the top is 2 times the bottom, minus the bottom is 3 times the top over the bottom squared. So that's the quotient rule. F prime g minus g prime f over g squared. Okay, now all you have to do really simplify the top. This is what, 2 plus 6u minus 3 minus 6u. And the numerator simplifies to -1. The denominator is just whatever it is. Okay, so practically you're done. So the last step is to write dy. dy is f prime of x dx. In this case, dy is whatever you have here times du, because the independent variable is no longer x, it is u. Okay. Now, what about this one? You use the product rule, so you can put a raised dot in between if it's helpful. So we are differentiating, which means we are finding y prime or dy d theta. So theta squared gives you 2 theta times sine 2 theta. Sine 2 theta gives you sine becomes cosine 2 theta, okay? Then because of 2 theta times 2, and then times theta squared. So I hope you see what happens. This gives you 2 theta times sine 2 theta. Sine 2 theta gives you cosine 2 theta times 2 times theta squared. And you can factor out the 2 theta. Okay, you can factor out the 2 theta. And practically you're done. This is dy d theta. So what is dy? The same thing times d theta. The same thing times d theta class. Okay, so I hope it's clear to everybody as to what's going on here. Okay. All right. I think we're ready to move on, class. We're going to look at more. Again, we are looking at differentials. So f prime of x dx. So in this case, again, your independent variable is theta. So you want y prime, which becomes dy d theta. Natural log, okay, flip over the argument. So 1 over sine theta times the derivative of sine is cosine, and that becomes cosine over sine or cotangent theta. You probably remember this. We have done this before. And so what is dy? The same thing times d theta. The same thing times d theta, class. So dy is whatever you got times d theta. Okay. All right. Some of you may remember we have done this class. Okay, I'm just refreshing your memory. This uses a quotient rule. The derivative of the top is e to the power of x times the bottom minus the derivative of the bottom is minus e to the power of x times the top. Okay, we've done this before. If you multiply this one by this one, you get e to the power of x. This one times this one is minus e to the power, let me just write that, minus e to the power of 2x. Let me write it at the top of it. So this gives you e to the power of x minus e to the power of x times e to the power of x is e to the power of x plus x, or e to the power of 2x plus e to the power of 2x, and the numerator is only e to the power of x. Now, so what is dy? The same thing, times dx. The same thing, times dx. It's pretty straightforward. Both questions, class, were done. I just wanted to remind you how you find the differential, if you will. Both questions were done before. All right. Here's the next one. Okay, the radius of a circular disc is given as 24 centimeters. Okay, so that's the radius. Maximum error is 0.2. We want to use the differentials to estimate the maximum error in the area, and then what is the relative error. We can, completely ignore part B for now. Part A, we have seen it, class. In short, we want dA. I hope you remember that we have done this. There's nothing brand new here. Okay, so basically the radius is 24, and the R, or delta R, is 0.2. The relationship between A and R, A equals pi R squared, and we want dA. We have seen the same question, slightly different numbers, same question. So part A is being repeated in essence, everybody. Same question we have seen before, okay? So we are dealing with that. So we are going to find A prime of R, okay, or dA dr, and if you recall, it was 2 pi R because pi times R squared becomes pi times 2R, or 2 pi R. So we know that. Therefore, dA is 2 pi R dr. Again, I hope you remember that. Replace the R with 24 and the R with 0.2. And there we have it, 9.6 pi centimeters squared. Again, you can change the pi to 3.14159, or you can keep it. Having said that, what is the relative error? The relative error is defined as this maximum error that we found over the actual area. So that is the definition, class. So relative error, okay, is the amount of error over the actual amount. The amount of error is dA, okay, and you probably remember it, even it's like the concept of a percent increase and percent decrease. Okay, so the top is the amount of increase, if you will. Okay, so percent increase or percent decrease refers to relative error. We had that in elementary algebra. So what was dA? Rather than looking at this, let's look at this one. Okay, I want to make sure you see that there's an easier way. What is dA? 2 pi R dr. What is A? Pi R squared. Let's go with that. So one more time, the A is 2 pi R dr, and A is pi R squared. So let's simplify it here first, 2 dr over R. So why am I doing it here? Otherwise, I have to divide this one, class. Otherwise, I have to divide this one by the area. I have to calculate the area. This is faster. Now I'm going to replace the dr with 0.2 and R with 24. And it becomes 1 over 60 precisely. And if you left it as that, it's fine. However, when it says percentage, you write it like this, and this is the percentage. And notice I put 1.64 because this is a precise answer, and I wanted to keep it as such. Okay, class? That's why I kept it as such. All right. We want to use the differentials to estimate the amount of paint needed to apply a coat of paint, which is 0.05 centimeters thick, to a hemispherical dome with a diameter of 50 meters. So first and foremost, R is 50 divided by 2, okay? And then, so think about the concept. When you put a coat of paint, you are changing the volume by that much. That's the idea, okay? So everybody knows the volume for a spherical shape is 4/3 pi r cubed. So for this shape would be what? The same thing times 1/2. That's one thing we need to know, okay? And so you're looking at the change in the volume in essence, where delta R or dr is 0.05 centimeters. Okay, so take a look and see what happens. Okay, number one, R is 50/2. 50/2 or 25 meters. Delta R is 0.05 centimeters. Okay, you have a choice. Change this one to 2,500 centimeters, or change this one to 0.0005 meters, because remember, 100 meter is 100 centimeters. Okay, that's why. So you can go either way. Just pick up your variable of interest, units of interest. So all of them are in meters or all of them in centimeters. That's the first thing. So the volume is 4/3 pi r cubed, okay, but it's half of it, class. Because of this, it's half of it. So I hope you see why we say it's half of it, okay? And so we want dV. That's all there is to it. So first we find dV dr, which is 1/2 times 4/3 pi, and r cubed, as you recall, was 3r squared. Okay, and so we get 2/3 pi. Okay, times 3r squared, 2/3 pi. So this is the simplification of these two. 2/3 pi, so remains 2/3 pi remains. R cubed gives us 3r squared, and so 2 pi r squared. What is r? Is 25 meters, remember that. But what do we want dV? So the same thing times dr times dr, the same thing times dr, 2 pi r squared dr. Now replace this with 25, and then this one with 0.0005. And that gives us 5 pi over 8, or 1.9635 cubic meters, okay? So this is an approximation. What is the exact amount, class? Can anybody tell me how we can find the exact amount? Precise amount of paint. Anybody? Well, in this formula, replace the R with 25, okay, 0.05, okay, 0.005, I mean. And then with 25, and you have the answer. Okay, so in other words, add this to it and calculate the volume, and then just plug in 25. Class, this is the answer, and this one is this one is supposed to be 25 plus this amount. Okay, so that's wrong. Okay, class. So that's the way you do the calculation. I want to look at the last question, class. The last question of a section says one side of a right triangle is known to be 20 centimeters. So one leg is 20 centimeters. Okay. The opposite angle is 30 degrees. And maybe we have a possible error of plus minus 1 degrees. We want to use the differentials to estimate the error in computing the length of the hypotenuse. And what is the percent error? So again, the second part, never mind. The first part is simply dy equals f prime of x dx in general. So first, let's do the drawing. And as you can see here, okay, so this is theta, okay. The opposite side is 20, And the hypotenuse, we don't know. We can give it any name, X, Y, Z. You choose anything you want. It makes no difference. We just know this theta is 30 degrees with a possible plus minus 1 degrees. That's the idea. So one leg is 20 centimeters, okay? The opposite angle is 30 degrees with a possibility of plus minus 1 degrees. So we want to know, okay, the length, the estimate in error in the length of what? X. So we want dx. I hope you see that what is given, what is missing. Okay, everybody? So having said that, we want to find that. So what is the formula that can relate all of this? We want to relate the theta and x in essence. Remember that. Okay? Because we want to find the x. All right? So I hope you see the easy way out. Sine theta is the opposite over the hypotenuse. So 20 over x, okay, or x is 20 sine theta, okay. So now x is a function of theta, class. X is a function of theta. That means x is a dependent variable, theta is the independent variable. So we want to take the derivative with respect to theta. So we want to get dx d theta, dx d theta, which is 20 times. Now cosecant theta, the derivative is negative cosecant theta, cotangent theta. Okay. And so what is dx? Dx is the same thing times d theta. Same thing times d theta. Okay. So this one is cosecant 30 degrees. Remember, cosecant is 1 over sine, 1 over 1/2 is 2. This is cotangent 30 degrees. Okay. And this is d theta. D theta is plus minus 1 degrees or plus minus pi over 180. Okay, class? Plus minus 1 over plus minus pi over 180. So I can't really emphasize this enough. I hope everybody is comfortable with that. Okay. So plug in, evaluate, and that results in plus minus 2 square root of 3 pi over 9 pi over 9. Okay. And so if you evaluated pi 3.14159, and it gives you plus minus 1.21 centimeters. So that means this is 20 centimeters, okay, with a maximum error of either adding or subtracting 1.21 centimeters, okay. What you probably want to write is this, class. Let me just do this. After this, I would write x equals minus 20 cosecant theta times cotangent theta times d theta. Put this one, class. And now this one is cosecant theta being 30 degrees or pi over 6, okay. This is cotangent of 30 degrees or pi over 6, and then plus minus 1 degrees is pi over 180. Now, what is the relative error? By definition is the amount of increase or decrease by the original amount, so dx over x, class, dx over x. That's it. And so if you want to go with precise dx that you found, or you can go with this, either way it's fine, okay, and you come up with this answer, okay, plus minus about 3.03 or plus minus 3%, okay, plus minus 3%. All right.